Recording in progress.
All right, let's get started. So last class, we talked about limitations of DFAs, and then we started discussing ideas for going around them, right? And many of you suggested various fixes, like, said, like, let's look at memory, then maybe giving the DFA read-write access to the memory, and also allowing you to read the input both multiple passes. And we said one way to do that might be you allow the head, the pointer where you're reading, to maybe move both left and right. In DFAs, you read a bit, move to the right, and forget about it. So here we're going to do both, move to the left and move to the right. And our goal today is to kind of expand on these ideas. We pretty much have the entire picture, and we'll present a very seemingly simplistic model. It's very, very simple, very local. But we'll see kind of why this is a single machine that is enough to really capture what we think of as computing. Okay, and this is how Turing machines are. And then we'll look at some examples, compare them to what we think of as modern computers. And then this allows us to develop a whole theory of computability. Okay, that's kind of where we're going. But before that, a few announcements. The exam 1 grades should hopefully be up by today evening. We're almost done. The TS are almost done with the grading, and once they're done, I'll release them. And remember, you have a week to submit regrade requests as always. Okay, so we'll release them today evening or maybe early tomorrow morning. But once they're released, you have a week to submit any regrade requests and do so on Gradescope. Okay. And also thanks to all who filled out the feedback form. It's been very helpful. Based on that form, it came to my attention that having office hours 2 to 3 on Mondays and Wednesdays kind of put many of you unable to attend my office hours, so I changed them. So there were other useful insights. Many of you liked the pace of the course. EdSTEM also seems to be doing well. And let's see, what else did I want to say? And for the question about what would you like to see more, it was kind of an even split between more examples and more kind of insights into some of the advanced nuggets I kept mentioning. So I'll try and include more examples. And for the advanced nuggets, I'll see if there's one way to maybe have a special session or something like that. Many of you expressed interest in that. I'll try and see if there's some way to do it. Okay. All right. Okay. So let's start with what we kind of said at the end of last class, right? So we said, intuitively, Turing machines are really just DFAs plus left-right movement plus read-write memory. Okay, so fairly intuitive kind of description, but let's make it formal. So the ingredients of the machine will be 2 things. So the first ingredient is, if I can draw a good rectangle, is what's called the memory tape. Memory or tape. And you can imagine Turing, when he proposed this in 1936, he taped machines or something like that was maybe a better term, but you can just really think of it as an array. Okay, so it's just a long array without any finite size, without any bound on its size. And at the start, we will assume that the input has been loaded onto the beginning of this array, the memory or the tape. Okay, so sometimes it's helpful to think of it as a tape because you really have like a head that is pointing in the tape and kind of moves around. So you can keep that mental picture in mind. Okay, so you have the input that has been loaded into the beginning of the tape. And then, there's a cell for each position. Like, there's something that you can store in each of these positions. And then after that, it's all empty. With this empty symbol just denotes that nothing is written there. Okay. And there's also this notion of states. And we will assume that the number of states is bounded, is fixed, and is some number k. Okay. So just like finite automaton, you still have a finite number of states, and you have this kind of input loaded onto a memory or tape. And you start with the head pointing to the start of the tape. Okay. Makes sense? And just for convention, again, there are various ways to kind of draw the same thing. Sometimes some things make, some calculations easier, others more little bit annoying, but we'll adopt the convention that there is a special marker, okay, which I'll denote by triangle, kind of tells you this is the start of the tape. Okay. This is just convention, like it tells you that this is the left end of the tape and there's no right end. It just keeps on going forever. All right. That's the basic setup. And now we come to the main thing that we have to do. So in each step of computation, so what happens in a single step of computation? So the machine that we design will decide to do something. And what is that something? It has to be describable in a finite sequence of instructions, right? And an algorithm has to have a finite description, even if it can operate on unbounded length inputs. So for a finite automaton, it was like the instruction said, okay, if you're in state I, and if you read with 0, then jump to state j. Okay. Something similar has to be done for Turing machines. So what would be something that you would say, right? So let's say you are in state I and read a bit, maybe a, let's say 0 or 1 for now. At the head of the tape. Okay, so head of the tape just means wherever your pointer is pointing to within this memory, right? You have this long array, and every time you don't make a decision based on the entire contents of the memory, you could potentially define something like that. But let's aim for the simplest possible model, right? The simplest possible one would be just like DFAs. You make your decision just based on what you read, where you are. Okay. So if you're, maybe the head is pointing somewhere here, you have to decide what you do just based on what you read there and what your current state is. Okay. So what are some things that you could do when you see this? Like you're in state I, you read something, you have to decide to do something. That's your programmable instruction that you're going to give to the machine. For DFA, as we said, it's just like jump to state J, move the head 1 step to the right. That's it. Okay. For Turing machines, given our insight that we want to allow the head to move left and right, read-write access, what are some things you could do? Any suggestions? Any suggestions? Like, just to extend DFAs. Well, DFAs at least did something, right? Which is they could potentially change the state they were in. You're in state 10 with 0, jump to state 21. Okay. So you could say, okay, change your state to something. Okay. And what else could you give as instructions? Yeah. Yeah, you can write something at the position you are in. Okay, only at the position the head is pointing to. Okay, so like if I'm here, I could read this, decide to write something. And what else? Any other things that we could do? Add, yeah? Move the head. Okay, so move the head for DFS, as I said, was only to the right, but we now allow, two-way movement, right? So we'll say move the head either to the left. We will denote this as L, either to right, denoted as R. And for convenience, again, this is not strictly needed, but it helps shorten some things. You just say either stay where you are. Okay, you can decide to just write something and stay there itself. That's also fine. Okay, so these are the actions, these are the allowed instructions we can give to the machine. Like, this is part of the description of the machine, right? Based on what state you are in and what symbol or bit you read, you can decide to jump your state to something else, write something, or even, maybe not write anything. Okay, or move the head in one of three ways. Any questions about this? Yeah.
We have the models for like the tape, but do we need like an additional structure to hold the state?
Yes. So the state is kind of like finite sized memory. If you think of it as like, like state control in some sense, it's fixed size, but the memory is actually can grow with the input length and can be unbounded, in fact. Okay, it's a good question. Any other questions? Okay, that's the intuitive picture. To formally define it, again, involves a little bit more notation, but it's fairly similar to how we defined DFAs. Okay, so here's the formal definition of Turing machines. So we will have k states. Okay, and when we talked about DFAs, we only focused on DFAs which were reading zeros and ones. Okay, and that was because we said at the beginning of the course itself that we can always assume everything is encoded as zeros and ones. But when we are talking about Turing machines, some things become a bit too tricky or kind of more tedious than necessary. So let us stick to allowing additional symbols besides zeros or ones, but still a finite sized alphabet. Okay, again, this is not strictly necessary, but makes it easier to see what is happening for the examples that we have in mind. All right. Okay, so you also have a alphabet sigma, which always contains the bits 0 and 1 and two special symbols, the triangle and the empty. Okay, so this is a finite alphabet, and triangle is kind of notation for start of the tape. Okay, so really it only occurs right here. We are not going to use it anywhere else. It's just to mark the beginning of the tape for us formally. Okay, otherwise you have to do some cases. Let's avoid that and just stick to this. And phi is notation for nothing is written. So that memory cell is empty. Okay. So initially you have the input, which is loaded onto the beginning, and then everything after that is just empty symbols. Okay. All right. So this is the alphabet, and then there is the transition function. Yes, so just as for DFS, the entire behavior of the machine was described by the transition function, right? You know, if you're in state I, bit 0, jump somewhere else, okay? Something similar is going to be specified, is going to be the description of the Turing machine, right? And we'll use this notation like Greek alphabet delta because, you know, it might get confusing with our notation for machines. So let's stick to this delta for the transition function. The input for the transition function, just as for the DFA, will be the state you are in, the state you are in, and the symbol that you're going to read. Okay. So it's going to be right, the set, you know, in name of the state that you are in takes a symbol and outputs some things, right? We'll parse it in a second, but it can tell you what state you go to, what symbol you write where you are, and the action of the tape head. All right, I'll explain this in a bit more detail. Okay, so there is left, right, stay, and a special thing called halt. Again, this is for convention, but let me expand on this in a second. Okay, so the transition function takes state, you know, maybe state I, you know, symbol from alphabet, and then says, you know, state J, another symbol from alphabet, and something telling you move head certain way. Okay, the transition function tells you exactly what you should do when you're in a certain state and you read a symbol. You can jump to some other state, decide to write something where you are, and then move the head certain way. So what is the certain way? You can move it left, you can move it right, you can stay where you are, and there's a special instruction halt or H, which is just stop doing anything afterward. Okay, again, this is a little bit like convention where you say you have dead state and so on, just halt, meaning you're stopping everything. Okay, any questions about this? All right, okay. So now that we have this picture, we can think of how the computation of the DFA would, of the Turing machine would work. So how would the computation work? You start with this as your initial configuration. Okay, you start with tape, this configuration. The head is pointing to the first symbol. Start with head at x0. Okay. State is the start state, which we'll think of as 0. Okay, so starting state. Okay. And then you have like a for loop essentially. Not for loop, but just like a while loop. You repeat maybe let's call this state S, that's our running variable, the current state. Let's say current state. You compute the new state, the new symbol to overwrite, and the action to take as dictated by the transition function from your current state and wherever your head is. Okay, so the tape, I'm thinking of it as an array, and head is where the pointer is pointing to currently. Okay, it's really just indexing into the array, right? So this is the memory contents viewed as an array. Okay. Okay, so there's this long array, which is our memory. We are calling it the tape, and the head points to somewhere in the tape, right? You read what is there. So tape of head. You look at your current state, and the transition function will tell you, okay, you have to go to a new state. There's a new symbol, and then action to take. So based on this, the next step would be update. Oops. Current state to the new state. Okay, and you rewrite what's at the head location. Tape head is going to be the new symbol. Okay, so maybe let me just say equal to be more clear. Okay, I'm rewriting what's there. And then you take action. So the action tells you what movement the head is going to make. Right, so this is like a case analysis. If A equals L, head equals max of 0, head minus 1. Right, you don't fall off the left end of the tape. No. If A equals right, head is going to be the old head plus 1. If A equals stay, you don't change anything. Okay, if A equals halt, then stop. Yes, stop meaning you break this outer loop. Right, until you see that construction, you just keep going wherever you are. Okay, any questions about the model? Yeah.
What exactly is the difference between like DFA's changing states and their head moving?
So the changing states part is kind of the same, I think, right? You're updating the state in a similar way. The movement of the head tells you what bit you read next. For DFS, it was preordained that you only read the next bit and you cannot revisit what was seen before. But for Turing machines, you can keep moving back and forth how many ever times you want. Okay, so that's the important distinction. The state movement, kind of the state notion conceptually is the same thing as for DFS. What's different is the head movement and the ability to write on the head, write on the tape. Okay, but still you're kind of making a very local operation. That's what's very interesting about it, right? Even though you're allowed to write, it's not as if I can write the entire memory contents to something new. I only get to write a single location. Okay, and I only get to move one step to the left or right based on what's my local view. Right, so Turing machine is a very, very local computer, and that's what makes it so useful, as we will see later on. Okay. Any other questions? Okay, it's not at all a far-sighted machine. It just makes decisions based on what it sees immediately. Okay. So that's a description of the machine. And let me define what it computes now. Right? So the description of the machine would be, you have states, you have alphabet, and the transition function. Together, all of that would define a Turing machine M. Okay. And once again, there is some convention we have to hold. So on an input X, if M halts on input X, then the output of the machine is all the contents of the tape until where your current head is. Okay, maybe your head is all the way in the millionth position, then the output would be the first million cells of the memory contents. Okay, wherever your head is, you output everything. Okay, so tape 0, tape 1, all the way up to tape head. Okay, so memory contents till where head is. Okay, so you might have written something past it, but maybe you moved the head back, but the output would just be wherever your head is. Okay. Again, there are various conventions. Most of them kind of end up with the same thing, but this is one convention which is kind of clean enough for us to use. All right. But there's one catch, your machine might not halt at all. Okay, it can keep looping forever. For DFS, this was never an issue because you only move the head right. So you will eventually reach the end of the input. And then you could say once you reach the input, that's the output. But your head could be just go left, go right, go left, go right, go left, go right. So you're just stuck there, not doing anything, right? So that's an important issue. And one of the reasons why Turing machines are powerful. So if M does not halt, okay, we'll have a special symbol to denote that it did not halt. Okay, it's like getting a code dump error, right? The notation we will use is this perpendicular symbol, or just like NaN or code dump. That's what you should think of it as. If it does not halt, we are just having a different notation for what the output is. Technically speaking, the output is only well defined when the machine halts. Okay. Any questions about the definition? Please let me know now, because we're going to discuss these things for the next 9 lectures. Yeah.
If it doesn't halt, like, when does this just not stop?
Yeah, it does not stop. Like you can have a program which just doesn't halt.
So how would you ever just like time out or something?
Yeah, I mean, you can say timeout, or you can just say it's undefined, really. So the way we define computability will kind of make it not important, make it not an issue in our definition, but it's helpful for us to have a notation to say, okay, this machine did not halt on this input. Okay. Any other questions? Right. And one thing to keep in mind is that there are some details or conventions we're using. Turing machines are, again, very robust to any of these conventions. You can have, adopt all kinds of things. They'll all turn out to be equivalent, but let's just stick to one of them. All right. Okay. So let's do a simple example. I will write down what the machine is, and you have to tell me, what it's computing. Okay. So it has a single state. The alphabet is the smallest possible one. You just have 0, 1, the start of the tape, and then the empty cell. The transition function does the following. I'll denote it as delta M. M is for the machine. If you're in state 0 and you read bit 0, then you stay in state 0, you write 1, move to the right. If you're in state 0 and you see 1, you stay in state 0. I mean, there's only a single state, so there's nothing you can do really. You write 0, move to the right. If you see the empty cell, then you don't do anything but halt. Okay. All right. So that's the description of the entire machine. So this is an algorithm now. It does something. And what do you think it does? If I give X as input to this machine, what's the output? X complement, right? It basically just flips the input. Right? So whenever it sees a 0, it's overwriting it as a 1. If it sees a 1, it's overwriting it as a 0. Okay? So Turing machines, under our definition, you will view them still as functions. Okay, they compute some functions. Given an input, they produce an output. But the output need not just be binary. It could be any of this, it could be any symbol from the alphabet, right? Because what you decide to write could be anything from your sigma, the alphabet. And union, this special perpendicular symbol, just denoting it did not halt. Okay, so if it halts, there's a nice description of the output. If it did not halt, then we just put perpendicular as a kind of a placeholder. Okay, so m of x equals the tape contents until the head. All right. Yeah.
So all the sigma star really you get zeros, ones, null, or the empty string?
Yeah, it could also be some special symbols. It makes a task easier. You could, if you really want to, get rid of all of them, may just work with binary. But I think this is much more, at least for Turing machines, is somewhat necessary to not go into that much detail. Okay. And just as we did for circuits and DFAs, we can define what it means to be computed by a Turing machine. Like a Turing machine, it's like a program, right? It gives us some kind of implementation for something. So we say a function, for now at least, which takes binary strings and outputs binary strings, is computed by a Turing machine M if f of x equals m of x for all x. Okay, so implicit in this definition is that the machine should halt on all inputs. Only then can we say that the machine computes the function f, right? So you have some specification, like think of flipping the input. That's a function. F of x is being mapped to the complement of x. That's a function. And we saw a Turing machine which computed exactly that function. Okay. All right. Any questions? Okay. So let's look at some examples, starting with just the simple flipping the bit, and we'll see. Just to get some insight, let's see how this definition allows us to immediately go beyond DFAs. Okay. So to that end, let's see. Make sure. Yeah. So there's something called a Turing machine simulator. I have an account for us there. I mean, And I'll share the account details on HSTEM so you can play with these too. So you can give instructions for simulating a Turing machine. The convention is a little different from what we have. Like you can specify a state name with a Q, and like a 0 or 1 tells you what bit, what you should do when you see that symbol. This is a new state, what you're going to write, and greater than means move to the right, less than means move to the left. Okay. All right, so let's say I load this as the input, and that's the tape. So in their convention, the tape is considered infinite on both sides, but let us stick to the case where it's only infinite on one side. It doesn't change how we do things. You can adjust the speed, and let's say you do plus. So instead of the head moving right, they visualize it as the tape moving to the left, but it's the same thing. Okay. Right, so accepted is just like saying, okay, it halted, and the output would just be from the start to where the tape is. Okay, so if I say show output, it will say, okay, 0, 1, 1, 0, 0.
Yeah, and it like moved back backwards. Is our output like
Yeah, to the head, like wherever the head is. Again, you could change it either way, but we are sticking to the case where it's up to and including where the head is pointed. So that's why I programmed it to move one step to the left.
in this case, like when we receive the empty
Maybe. But let's say you're not giving it, like, let's say just do this, what happens? Okay, so it moves one step to the right and then comes back and then halts. Okay. All right, so very simple machine, very simple execution, simple to visualize. All right. Okay. So now let's do something more interesting, right? So when we talked about the limitations of finite automata, right? We showed that certain functions, simple functions that we would care to compute were not regular, were not computable by DFS, right? We use the pumping lemma to show this. And the first example we had for that was the majority function. Okay, so recall the majority function, which was defined as, you take a bit string as input, 1 if there are at least as many ones as zeros, right? Either there are more ones or at least as many ones as zeros, and 0 else. Okay. And we use the pumping lemma to argue that, recall, DFAs cannot compute majority, right? So this is not a regular function. Okay. Now what we're going to do is show that Turing machines can actually compute this, and they can do this in a fairly intuitive way. Okay. So any suggestions? Again, I don't want gory details. Think of really, some sort of high-level instructions you could give to a machine which can only look and decide what to do based on where you are, where the head is pointing. Okay, that's the most important constraint to keep in mind. You only get to change what is immediately beneath you, and you only get to decide based on what is immediately beneath you. Okay. So any ideas for how to implement majority under these constraints? If I ask you to write a programming, if I ask you to write it in Python, you'll say, okay, I equals 0 for every 1, just increment I by 1, and then check if it's more than the length, half the length, right? That's your 4-line Python program. But now if I ask you to do it on a Turing machine, what would you do? Any suggestions? Yeah? Okay. Okay, so I think I get what your suggestion is. The idea is, maybe you swap things so that all the zeros come before all the ones, and then you kind of check the more ones should be at the end of the thing. Okay. Intuition, I think what you're saying is we can try to match 0 to a 1. Right? If you match 0 to a 1, try and match each 0 to a 1. At some point, if you run out of ones to match, then there are more zeros than there are ones. Okay, does the intuition make sense? Okay, so just building on the idea. So first, let me write it in words, and then we have to think a little bit on how we're going to implement it in this sort of local computation, right? The idea, try to match zeros to ones. If you're unable to match a 0, then output then there are more zeros than ones. Okay, so you see a 0, you go looking in the entire input for a 1 that you didn't kind of use up already. Okay, if you find one, just mark that one as already seen. This 0 has already been marked as well. And then you again start looking for another 0. Okay, so that's the intuition. And now we can kind of implement it in steps, right? So the first step is you scan to the right until you find a 0. Okay, this is again high level enough, but still not like saying, okay, add counters or something, right? It's something that you can easily implement with like a single state or 2 states on a Turing machine, right? In a state, keep skipping until you see a 0. Okay. If no 0 is found, then what should you do? Suppose the input has no zeros. What should you output? What should the output be? 1, right? That's the definition of majority. There are no zeros, so there are definitely more ones than there are, at least as many ones as there are zeros. Okay, but there's one annoyance because of the way we defined our output. So we'll just say clean up the tape and return 1. Meaning, you have to make sure that you sort of empty the tape, or even if that's not needed, basically wherever the head is, it's at the beginning and it has 1 written there, right? Because the output is whatever is on the tape until where the head is. Okay. At this point, we know what the output should be. We should just make sure that the tape reflects the output. All right. And if yes, a 0 is found, what should you do? you kept scanning until you saw a 0 in some state. What would you do then? Think a little bit more detail now. Like, what would you instruct the Turing machine to do? Any suggestions? Yeah?
You could write a empty character there and then scan for a 1.
Yeah. So instead of writing an empty character, let me kind of, just for pedagogical reasons, let's say mark the 0 as seen. Okay, and if you use empty character later on, you might get confused when you reach the end of the tape too. So you have to be a little bit more careful. So let me just say mark the 0 as seen, meaning you're creating maybe, let's say, a new symbol, which like 0 dot or something like that, which tells you, okay, this 0 has already been taken care of. All right. And then what should you do? You found a 0 which has not been seen before. You're seeing it for the first time. So what should you go looking for next? A 1, right? But should we start looking for a 1 right away? Yeah.
Is it reasonable to like work backwards?
It is. So the only, again, there are various ways to code it up. So you can't just say, okay, go look for 1 from now on, right? What if, there's all 1s and a 0 at the very end? Right? You have to look in the entire string for a 1, right? So you basically have to scan the input to see if there is a 1 that has not been used up or marked before. Okay. So you'll say, maybe one easy way to implement it is go to the start of the input. Again, I'm going to write some compound instructions and we'll see how to like just implement it directly. Scan the input to find a 1. Okay, so you go to the start and then start looking for a 1 to the right. If 1 is found, what would you do? Look for a 0, but we should make sure this 1 is kind of marked up, right? So mark this 1 as seen and go to start. Okay. And if 1 not found, what would you do? If the 1 is not found, then what happened? So you found a 0, which was unmarked, but there was no 1 to match it with. What would you do? We had to return 0, right? So the head might be all the way somewhere we don't know. So we just have to kind of clean it up. So clean up and return 0. Okay. Yeah.
If we have like our tape,
Symbols.
and like the head is like at a position, is that the same as just for 1?
Yeah. So empty is just like nothing's there. Okay, but at least the way we are going to do in our examples, we'll make sure kind of at least it's written up reasonably well. But the convention would be that then the output would be exactly just 1. Okay. All right. And we are going to do a couple of examples, which I think it's really, to me at least, it's fun to program Turing machines because you have to think about computing in a different way. Not because you had to come with these tedious sort of states and so on, but you have to think about algorithms which have a very local view, right? Which is a conceptually very different challenge. Okay. And we'll do a couple of examples as a proof of concept of the things that Turing machines can do. All right. So here's what this is: a reasonably local algorithm in the sense that it kind of doesn't, it's only doing something very, very, only looking at what's happening. And you can load this up. So let's say I load this and Okay, you can see that, I have the states which are, the initial state is Q find 0. That's my name for a state saying, okay, go looking for a 0. If you're looking for a 0 and you find a 0, then you have to, you jump to a state which says go to start and then look for a 1. Okay. This go start 1 is our shorthand for saying, okay, you have to enter a phase where you have to go to the start of the input. And once you reach the start of the input, you have to jump to start looking for 1. Okay. And this A is kind of our notation for this symbol has already been seen. And marking this 0 has been taken care of. Okay. And then the, oops, let me not overwrite it. And the input head is moving to the left, right? You see a 0, you have to go to the start. So I'm just kind of already moving to the left. Okay. The next instruction is saying Q find 0. If I see a 1, there's nothing to do, right? You just leave it as it is and move 1 step to the right. Okay. And if you find if you're looking for a 0, but you see a marked symbol like A, then you don't do anything, just skip to 0. Okay. And if there is no 0 is found, then you enter accept. All right. So all of these instructions are kind of very bit tedious, but at least intuitive and match what we described as our algorithm to do, right? The next lines return us to the start of the input and ask us to find a 1, right? If you say go start 1 and you see a symbol, go to the left. Go start 1 and you see 1, just go to the left. Go start 1 and 0, go to the left. And in this simulator, the underscore denotes the start of the tape, basically. Okay. So you just do that. Once you go there, you found the start of the tape. So you just leave it as it is. And you enter a state asking you to look for a 1. Okay. So it's almost like whatever, how many of our instructions you have for implementing this. Okay. But the logic is essentially the same. You're implementing each of these things by state transitions. All right. I don't want to go into, maybe all of the details because I don't think they're very important, but the main thing is that you can do it. Okay. Let's just see it in execution. I think that, is probably just as helpful. It's now looking for a 0. It found a 0. So it marks it, goes to the start of the tape. Then it says, okay, I have to find a 1 now. You can see the state is written up there. Q find 1. Go find a 1. Okay, found a 1. Go to the start and start looking for a 0. All right. Even faster. All right, now it has going to look for a 0. It's going to say, okay. Didn't find anything, so you have to accept. So he's cleaning up the tape and then just writes 1 and stops. Okay, yeah. Yeah, so A is part of the alphabet now. So the alphabet would be 0, 1, A, and this dash, which is their notation for empty cell. Yeah, we are allowed to add alphabet. Again, technically, you can make everything binary, but having it this way is kind of helpful, at least for visualizing and understanding what the machine is doing. So you can have symbols in the alphabet, but there just have to be a constant number of them. You can't have like infinite strings or something. Okay. And let me just maybe show what happens if you have maybe all ones come first and then you have many, many zeros. I'll speed up this a lot. Okay, so run. Okay. Again, it's kind of amazing that just by doing this local thing, you're able to compute this. Okay. All right. So let's take a 5-minute break. When we come back, I want to do one more example of something that DFS could not do, Turing machines can, and then we'll start discussing the implications and the things that this model will allow us to do. All right. Okay.
Recording in progress.
Okay, so let's do one more example to just kind of get a sense of Turing machines. I mean, it's really like a new programming language, right? So when you learn a new programming language, you might try some simple hello world programs in a new language to check if you understand the syntax. So let's do one more example, which was the palindromes. Okay, and I can define it as a function or a language. So let me define it as a function for now. And no, actually, let's just, so palindrome of x is 1 if x equals reverse of x and 0 else. Okay. And again, this was another example where we use the pumping lemma to say that DFAs cannot compute palindromes. Okay. And my claim is that, I mean, we'll see, no surprise, that Turing machines can actually compute it. Okay. So now I'm asking you to write me a program in this new programming language, that of Turing machines, to check whether or not an input x is a palindrome. Does it read the same from left to right as it would from right to left? Right? You know, is this the same as this? How can I check or implement this using a Turing machine? Any suggestions? Again, let's start with the high-level description about how you could do it potentially with this local steps, and then we'll try and code it up in a little bit more detail and then a bit more detail. Yeah. Exactly, right? So the intuition is that palindrome means that the starting bit should be the same as the last bit, right? Because x and reverse of x should read the same. X should read the same when you go left to right and right to left. Means that the first bit, the 0th bit, should be the same as the last bit. Okay, the one position from the starting should be the same as the one which is one position from the end. Okay, so you need this one to match this one to match this one, and this one to match this one, and so on. Okay, so the idea was kind of do something a little bit similar to what we were doing, or at least inspired by what we were doing for majority, which is when the idea is check bits at both ends. If they match, mark them and look for next. Okay. And if they don't match, of course, you know that it's not a palindrome, so you should output 0. Okay. All right. So you can say, so here, let me, for once, do it in a bit more detail. So let me ask you a question. How can you check if x0 is same as xn minus 1? Okay, so now I'm asking, like, somehow tell me more concrete instructions you would give. How would I check the starting bit is the same as the ending bit? Think of breaking it up into a little more detail. Yeah. Exactly, right? So you remember what the first bit is, in this state. If the bit is 0, you say, okay, I'm trying to match a 0. If the bit is 1, you'll say, okay, go to a state which tells me you're looking to match a 1. Okay. And at the same time, we'll mark the first bit as seen. Okay. And then keep scanning right. Oops. Until you reach end. Okay. Again, keep scanning until you reach end is just saying you keep skipping zeros and ones and mark symbols until you see the empty symbol. If you see the empty symbol, now you know that you reached the end of the input. Okay. And then you say, okay, move one step to the left and see if it's a, whatever thing that you're looking to match. Right. Okay, so you look if it matches what you're looking for. If yes, then you go to the start, try to find the first unmarked symbol, then repeat. If yes, go to first unmarked symbol. Repeat. Okay, if no, let me just say clean up output 0 halt. Okay, so in this current description, there are some border cases that are not covered, but I think we captured the main thing that you have to do. Right? You keep scanning until you see an unmarked symbol, try to match. If you match, you mark both of them, kind of go to the start, find the first unmarked symbol, repeat. Okay, so let me kind of, maybe write down a couple of other instructions here. So my alphabet is going to be the usual 0, 1, the end indicator, the starting indicator, the empty cell, and a special symbol A, which is going to tell me, okay, this symbol has already been seen. This is our notation for marked. Okay. And Yeah, so let's say you see this x0, you'll say you start in state 0. If you see a 0, you enter a state which tells you go to end while you're still looking for a 0. Okay, you remember that, okay, you saw a 0. Now I'm going to the end, but I'm trying to look for a 0. And since this symbol has already been seen, I mark it, meaning I overwrite it with our special symbol A, move to the right. Okay. Similar way, if I see a 1, what should I do? You go to the end, but now you have to remember that you're trying to match a 1. Okay. And then AR. Right. So remember symbol seen, mark it red. All right. Okay. And you can kind of break up all of these things into somewhat modular pieces, right? So what does go end, or what is go end 0 supposed to do for us? It has to keep scanning to the end, right? If I see a 0 when I'm in this state, what should I do? And I'm here, I'm looking for go end 0, but I see a 0. What should I do? You should just skip, right? Because you haven't reached the end. The mnemonic is that go end 0 is telling me go to the end of the input. Recognize when you reach the end of the input and check if you matched a 0 or not. So if you haven't reached the end, then you just skip it. Okay, keep moving to find the end. All right. And if I'm in the state go end 0 and I see an empty symbol, then what should I do? Well, now I know I've reached the end, so I should check if the symbol before that is a 0 or not. Okay. And I can say, okay, now that you reach the end, I'm going to enter a checking for 0 phase. So check if the bit you see is going to be a 0. Don't do anything for the symbol. Move 1 to the left. Because this is saying found end. Yeah. Yeah, it's going to come up. You know, again, you have to replicate all of these things for 1. Okay. All right. And then, you know, if I'm looking for check 0 and I see a 0, then what should I do? You're looking for a 0 and you found a 0. So that means everything is fine. So you have to kind of go to the start and repeat the entire thing, right? Okay, at least this symbol matched up. Now you have to go to the next step, try and match the next symbol. Okay, so I'll say go to the start. And since I found a match for this, I can kind of erase that symbol saying, okay, this is a new end. This has already been matched. Like, let's say I matched x0 with xn minus 1, then I can forget about this. I go to the left and try to match x1. Okay. So rewrite it with the empty symbol and move to the left. So found a match. Okay. Whereas if I was in check 0 state and I found a 1, what should I do? we kind of know the function's output at this point, right? So these two things did not match means I should just output 0. Okay. So I can't just say output 0 because the way the programming language is designed, you have to do some processing to get to that. I'll say enter a state, write 0, and then do nothing, and then you can do whatever. It doesn't matter, I think. So this is our code for cleanup tape and output 0. Okay. All right. You have to still write down what you would do to kind of implement this functionality. How would you do go start and so on. Okay. So let me try and do just one more, which is the go start part. So what is go start supposed to do? Where your head is, it has to move to the first unmarked symbol, right? So you're trying to find the first unmarked symbol, but you see a 0. What should you do? Just skip it and go to the left. Okay. So just stay in the same thing, left. If you see a 1, again, you still haven't seen the starting of the first unmarked symbol. How would you know you've seen the first unmarked symbol? Is basically you overshoot it and you see a marked symbol, right? So if you see an A, then okay, I'm where I am. So you go to start, meaning the real starting state is 0. Just leave it as it is and move the head to the right. Kind of, I'm resetting the entire computation now. All right. So I saw the kind of a marked position. So I know that I have to repeat the whole thing, the whole loop from the beginning. So I enter the state 0, leave the marked symbol as it is, move the head 1 step to the right. Okay. So this is, maybe I should just box these things, because there's some logical grouping you can do. This modularity is very helpful in understanding what Turing machines do. Okay, so each of these is kind of implementing a special instruction. Find first unmarked position. Okay. And then you have to implement the other stuff, how do you do write 0? You have to write all the analogous things for go end 1, check 1, go start, and so on. Okay. Does it make sense? All right. And if you do the entire thing, what you end up is a Turing machine for palindrome with the alphabet being something like 0, 1, the standard 4 things, plus just the special marked symbol, and the number of states is going to be 10. You could probably do better, but 10 is one way to do it. Okay. And again, if you see something problem like this in the homework or in the exam, there may be 1 or 2 like this, just to kind of get a sense of the power of them, right? Then you could either write down instructions at this level, or you can just stick to something like this, as long as it's reasonably modular and kind of something at this level of detail will be good. You can't say, okay, add up the numbers and you'll get the answer. That's unacceptable because we are trying to see how you would add up numbers. So you can't just say add up numbers. But this notion that, okay, I can match and then, cancel them out, mark them out, that makes sense. Okay, so something like that is what we are looking for. All right, but it's fun to actually see them in action, even the simple instructions. So I did code it up, but I need a palindromic thing to make it an interesting example, maybe. Let's say, this is a palindrome, I'm guessing. Yeah. Okay. Here you can see, like, there's all of these, the exact same things that we did. So go check 0, comma a would do something, go and would do something, go and 0, 1 would do something, exactly the instructions that we had. I just coded it up in this simulator. The simulator has a slightly different convention, like, basically one line denotes the input, the second line is the output, but it's how somebody implemented it. Is now it's going to the end. It remembers that the starting bit is a 1. It's looking to match a 1. This is the empty symbol. Say enters check 1, found 1, says go to the start. Found that. So now it says, okay, look for a 0 again. Okay. All right. Yeah.
Is there a reason why after finding the first match, instead of you don't just check like
So that's what we are doing. The way we are doing it, at least in this implementation, is once I see the n-1 thing, I'm erasing it completely so that I know what is n-2.
instead of like going all the way back to 2 and then going back to check?
Oh, yeah, definitely. You could try and do that. So you're saying basically instead of like going back to the beginning and then starting from 2 and this, once you find the end, why don't you just go one step back and then look for it? I think you can do that. Yes, definitely. That would save you some, I think you would probably do half as many runs, but the instruction set would have to be probably a little bit more complicated. Okay. Yeah.
Did we ever specify how to get to that accept state? Because I noticed at the end we had.
Yeah. So basically, when you had to write it down. So when you're in starting Q0 and you see the empty string, that means that everything has been matched. And then you say accept, right? Basically, I start to match 0 to n-1. Those things are marked. Basically, when there are no more unmarked symbols, then you know that everything has been marked. You should accept. Okay, it's a good question. Yeah.
Does this handle like odd like
I think so. Well, let's see. Oh, I see what you mean. Yeah, I think if it's odd, then yeah, this might not handle it. Okay, never mind. But let's say we only restrict to even. If it's odd, then you have to, I think you have to enter a special state for that. Yeah. Basically, if you immediately see an empty symbol, then you say, okay, if there's nothing in between, then do something. But good catch, yeah. All right, okay. Okay, let's just do one thing more. It's very pleasing to watch this in time lapse. All right, if you're someone like me who likes Turing machines, that's what I do in my spare time. Watch time lapse videos of Turing machines. Okay, so this is just to give you idea of what you can do with this new programming language, but it still seems a far cry from something like Python or any other language, right? Even probably something like Lisp seems better than programming Turing machines at this point, okay? But let's see what we did so far, right? We kind of defined a new model of computing. And this was Turing machines, right? And we demonstratively saw that Turing machines are indeed more powerful than DFAs, okay? And to that end, let's recall, what was this definition? Yeah, so let's recall this guy. Okay, we said a function is computed by a Turing machine if something nice happens. Okay, and in the same way, you can also, as we did for DFAs, you can also define something similar for languages, right? Languages and functions are similar. So if you have a language, L is recognized or computed by a Turing machine M if X belongs to L implies M of X equals 1. If a string is not in the language, then the machine should halt and output 0. Okay, that's an important distinction. So the machine should always halt on the input, and if it's in the language, it should output 1. If it's not in the language, it should output 0. Okay, there's a slightly more general definition, which we won't look into, but again, it's a very interesting one, where you can drop the second condition and say it's either 0 or does not halt or something like that, but let's not worry about that. Okay, and so Turing machines is essentially a new programming language. It's a very simplistic programming language. No abstractions, really. All you have is access to a single array, which you cannot even like jump randomly, just index or just move one step to the left or to the right. Okay. Now you can imagine what we think of standard, primitives that we use, right? You can have NumPy, and so what does it allow? One of the most powerful things that it allows indexable arrays. Okay, basically this was something that people suggested, I think in last lecture, to allow random access to the memory. Right now we're saying, okay, just move one step to the left, one step to the right, but you can just say, okay, what is in location 1000? Tell me what it is. That location could also be a variable and not just some fixed number, right? What is in location, 10 times I, where I is computed in some other way. Okay. And as it turns out, it requires some effort, but Turing machines can implement random access. And this is something you will see in the homework, but Turing machines can actually implement random access. They can simulate an ability that we take for granted, which is, okay, index into the array. It seems kind of hard because you're only moving left and right, a single step at a time. But you can say, okay, I give you an input saying description of an integer. The Turing machine can immediately tell you what's in that location in the array and end with that as the output. That is possible. Okay. But still, if you think of your favorite, programming languages, like, let's say, you might have, tell me some programming languages. C++, maybe Java, maybe Python. What else? Okay, no functional programmers here. OCaml. Okay, I'll start with my favorite, which is Lisp. Okay, all of this, they have so much more seeming power, right? Why would you ever think of this dummy programming language, right? Well, there is a reason why we do it. And this is one of the most important theorems that we are not going to prove. I mean, this is one of the most important theorems ever, but this is also a theorem that we are not going to prove. Sorry, I had to keep the phone on. Okay, for every, let me take a Python program. P, there exists a Turing machine M such that on all inputs, the output of the program is exactly the same as the Turing machine. Okay, the Turing machine can simulate your Python program exactly. You give me a Python program with 100 lines of code, maybe there's a Turing machine with maybe 1,000 lines of instructions, but it is going to be able to do exactly what your Python program is going to do. All right. And not only that, you can do this simulation reasonably efficiently compared to how primitive this language is. If your program P takes T steps of time, T units of time, T operations, then you can do it with a Turing machine that takes T squared time. Okay, it's not just true for Python, it's true for every one of these languages. Turing machine can simulate all of them. Okay, kind of perplexing that this is true, but it is true. It's not something we will prove, but we'll take this for granted and then see what it implies for us in terms of understanding what is computable and what isn't. Okay, any questions about the statement at least? What I find really surprising is this, not only is it possible, but it's possible, it's almost, it says quadratic blow up, which seems amazing, right? If you think of majority, the Turing machine that we did, it was kind of doing multiple passes. So it was like a quadratic time algorithm. And we're saying, that dummy simulation is probably as worse as it can get for any complicated program you might have. Okay. Any questions about the statement? As I kept saying, definition is more important than theorems. The definition of Turing machine extremely important. This theorem extremely important, and then we'll talk about some implications. All right. Given this, we can now sort of modify this definition and be brave enough or presumptuous enough to drop by a Turing machine completely. Okay, so we're going to say a function is computable. Okay, it's computable, period, not by Turing machine, but any machine that you want. If is computable, if there is a Turing machine M which computes it. All right. Okay, this is kind of, our assumption that something is computable if and only if there's a Turing machine which can compute it. And there's strong evidence for it because, any sort of high level language that we might have, we do think there is a way to just simulate them by a Turing machine. Okay, which is kind of counterintuitive. And to stress this counterintuitive nature, you can think of adding extra power to Turing machines, right? So let's say, someone asks you, I ask you again, just to brainstorm, I tell you, can you tell me ways to go beyond Turing machines? So it was a pretty rudimentary model, right? You just did one step to the left or right, small state, and there was a single memory tape. What are some ways you can allow additional power to Turing machines? Just think of some things. Yeah? More heads. Why should you only have to look at one position and decide your entire computation based on that single bit, right? Which is very restrictive, right? Often when you think of your program state, it evolves based on a variable which can be many possible values. For us, the program state changes only based on a single bit, single symbol. So you can say multiple heads. Why stop at multiple heads? You can say, why don't I have multiple tapes? Maybe just instead of having a single long array, you have many arrays. Maybe accountably many of them also. Okay, all of these are seemingly more powerful, but every one of them can be simulated by our plain Turing machine. Okay, just our simple definition of Turing machine can capture all of these additional things. All right. And this leads us to another sort of postulate or hypothesis or law of nature, what you can have different names for it, but it is called the Chuch-Turing Thesis. All right, so remember the physical extended Chuch-Turing thesis, which said, anything computable with some number of resources should be computable by circuits with roughly the same resources. Chuch-Turing thesis is something even grander, I would say, because it says every function that is computable by physical means. Okay, take a quantum computer. It can be simulated by a Turing machine. That's a theorem. You don't need to assume that. That is something that we can prove. Okay. This is a hypothesis and not a theorem just because it's saying something about the physical world. Right? It's a law of nature. It's like saying, when you drop an apple, it's going to fall to the ground. If you drop it on Earth, of course. But it's the same thing. Anything computable by physical means should be computable by a Turing machine. Okay. So this simple definition allows us to reason about what we can actually compute. And maybe that should answer all of our questions about computability and what we can and cannot do with computers. Okay. So we'll take this definition as a starting point, and this implication or this assumption that they're as powerful as anything else computable by physical means, and investigate it over the next 8 lectures. All right. Okay. So I'll see you all on Monday.